talk if you saw that at 1 o'clock. But just a little brief background about what dark matter is in general. So we do know a few things about dark matter. So it doesn't emit or reflect light, which is one of the reasons why we call it dark. We know that it does interact gravitationally with regular matter. And it accounts for most of the mass in the universe. So about 85% of all of the mass in the universe is made up of this dark matter, and the matter we're used to, like things made of electrons and protons, things that are familiar to us, are only about 15% of the entire universe. So unfortunately, what we don't know is what dark matter actually is. We have a pretty good idea of a particle candidate, which we refer to as a WIMP. This just means a weakly interacting massive particle. And the specific type of WIMP I'll be talking about today is the neutralino. So, looking at all the evidence we have for the existence of dark matter in the universe and the best guesses that we have to what it is, we can start looking for it. There are different types of ways to look for dark matter that Trevor talked about earlier, but the type that deals with my research is indirect detection. So neutralinos are majorana particles, and all this means is that they're their own antiparticle. So when two neutralinos come together, they annihilate and give off different particles, which we can then detect. So since dark matter, like I said, interacts gravitationally, we expect it to behave just like regular matter does when it encounters a gravitational well. So we know that like we're attracted to the Earth, so is dark matter. So we expect that dark matter particles will gather at the centers of very massive objects. So things like the center of the galaxy, the center of the sun, and even the Earth. So as these dark matter particles build up in these heavy objects, we expect them to annihilate, give off products which we can then observe, which are normal particles which we can detect. So there are lots of different products that can come from this process, but the type of product we're interested in is antimatter, and more specifically positrons. And just a little more background, this is about cosmic rays. Cosmic rays are just particles that come from elsewhere in the galaxy. We get a lot of them here. At the top of the Earth's atmosphere, we get about 1,000 cosmic rays per meter squared every second. Most of these cosmic rays are relativistic, so they're very high energy. About 90% are protons, 9% are alpha particles, and the rest of it is heavier ions and isotopes. So no one is really sure where these cosmic rays come from, but we have a pretty good idea that they probably come from energetic astrophysical objects like supernovae and pulsars. And there are two main types of cosmic rays that I'll be talking about. One is primary, and those are just cosmic ray particles that come to us from the source. And secondary cosmic rays, which are created when primary cosmic rays interact with matter in the interstellar medium, or ISM. So, like I was talking about, we look for dark matter particles using indirect detection, and these are a couple of experiments that are looking for evidence of that kind of process. So the first one is PAMELA. It was launched back in 2006, and it orbits the Earth, and it takes a look at the entire sky. And Fermi, which is formerly known as GLAST, or the Gamma Ray Large Area Space Telescope, which was launched a couple years later. It is a little bit different from PAMELA in that when it detects a particle, it can't tell the charge of the particle. And so when we see a positron or an electron go through the detector, we don't know, was it a positron or was it an electron? We just know that we had a particle of this mass and this energy. So what have PAMELA and Fermi seen? Well, this is a graph that shows the positron fraction on the y-axis, and this is just how many positrons we're getting divided by how many positrons and electrons that PAMELA is seeing. And then along the bottom is the energy of the particle. And so you can see here that the black dots are the old data sets from other experiments, and the red data points are PAMELA's data. And so if we expected that only secondary positrons are coming here, we would expect that our data kind of falls off as our energy gets bigger and bigger. However, you can see that it definitely doesn't fall off, but PAMELA and the other experiments are seeing that it kind of turns upward at about, starting at about 10 GeV and going up to at least 100 GeV. And Fermi sees something really similar. So we can't plot the positron fraction since Fermi can't tell the difference, but we can just plot the flux of either positrons or electrons that we're getting versus the energy, just like before. And you can see this blue dashed line. This is the model of what we would expect to see if it was only secondary positrons. But you can see from the red data points that Fermi is definitely seeing something weird as well. So what can we get from these results? Well, we don't know where these positrons are coming from, and there are a lot of different options of where they could be originating. So one of those is production in pulsars. Pulsars, we don't have a very good model for them. They're very exotic type of astrophysical objects. There are a lot of models for them, but none of these published models can explain the positron excess that we're seeing. Another possibility is that there's some other primary source, which just means there's some other object in the universe creating these positrons that we're seeing. We might not understand how particles travel through the universe. So as you might imagine, it's a really complicated process for a particle to be created and then come to here at the Earth. And so maybe we don't understand how that really works. And what's most important to us, maybe these positrons are coming from dark matter annihilations. So that brings me to our project. So what we're going to be doing is using galprop, which I'll talk about a little more in depth. It's a computer program to calculate positron backgrounds, so what we would expect to see from the background emissions. Next, we're going to use DarkSUSY, which is another computer program, to calculate what would we expect as in terms of a positron signal from dark matter annihilations. And then we're going to say, well, can dark matter annihilations really explain those extra positrons that we're seeing? And if so, what kind of characteristics would our particles need in order to observe that kind of positron excess? So galprop, like I said, is a computer code. It stands for Galactic Propagation, developed at Stanford by Strong and Moskalenko. It's free, available to anybody on the internet. And it models cosmic ray diffusion and interactions in the galaxy. So basically it tries to incorporate all the astrophysical data we have, any objects we know of in the universe, what are they producing, what kind of interactions do those particles go through on their way to Earth. And it also includes different theoretical developments. So like I said, the models we had for pulsars and other objects. So in a nutshell, galprop is solving this equation, which is rather intimidating, but each term broken down just represents a process that a particle will go through, possibly on its traveling through the universe. So after the equal sign, the first term just represents our source term. So this is kind of how many particles are being put into the universe by different objects. Then the second term represents diffusion and convection. So this is basically the motion of the particles through the universe. The third term deals with reacceleration. All this is the particles gaining more energy somewhere along their path through the universe. So being heated up or accelerated in the universe. The fourth term, starting on the second line, deals with energy losses. So as it travels through the universe, we can have scattering, different scattering type events that will make the particles lose energy. And then the last terms are just nuclear fragmentation and radioactive decay. So galprop uses a Crank-Nicholson method to solve this equation. And all it is a method to solve partial differential equations. And so it's called a finite difference method because whenever you see a derivative expression, you just replace it with a finite difference expression, which is that limit that we learned in calculus before we actually learned how to take a derivative. And we call it implicit because it looks at both an initial state and some later state. And this solves a lot of problems that we would get from explicit methods with our solution varying wildly based on parameters. So when we use galprop, there are about 208 parameters or running options that you can put into this program. And since it's modeling particles traveling through the universe, this kind of makes sense because there's a lot of stuff going on. And we have relatively large control over the parameters in the program. So just as an example, we can talk about like the geometry of the model of the universe we're using. We can talk about particle energies, what processes to include. So in that transport equation, we can tell galprop, do we want to include this specific process when we do our calculations? And we can change the supernova intervals, how often do they happen and how long do they last, and many, many more. Galprop also uses sky maps, which are just maps of the sky, so that's what you would think. It shows where different objects are in the universe, and most of these are left alone for the most general purposes. So we give Galprop its input, and then what we get back are different particle fluxes, or just how much of the particles are we getting here at the Earth. And so we can look at the flux relative to different things, so the proton abundance, any other cosmic ray particle abundance, or just flux alone. And you can actually use Galprop's WebRun application, which anybody can go on and use to gather the data without actually having to ever mess with the actual program. And so here's an example of what you might see from Galprop. So what I have here is the flux of electrons, which are the green squares, and the flux of positrons, which are the blue diamonds, versus the energy. So now we can take that data and calculate the positron fraction. So if you remember when we looked at the PAMELA data, we were looking at the positron fraction on the y-axis and the energy on the x-axis, and that black line is kind of what we would expect from secondary processes only. So that's representative of a model used in previous literature. And so over here I calculated the positron fraction for just a default parameter list, and you can see that they're relatively similar. So the next steps that I'm going to take in my project are continue to work with Galprop. So I've had some issues with the actual program, which is why using the WebRun is really nice. We need to determine exactly what parameters do we want to use to calculate the positron backgrounds. So what I'd like to do is determine what parameters have been used previously in studies so that I can do the same and then be able to compare my results to theirs. And then what we're going to do is isolate the positron fractions that are calculated by Dark Suzy, the second computer program, and to run models to determine whether neutrinos can actually explain the positron excess and what characteristics it would need to have to do so. So with that, I'll take any questions.